All right, Chapter 2, Video and RF Radio Frequency Amplifiers. Learning a chapter. To completion of the chapter, you'll be able to define the term bandwidth of the amplifier, determine the upper-lower frequency limits of the amplifier frequency response curve. List of factors to limit the frequency response of in an amplifier. List two techniques to increase the high-frequency response of the radio amplifier. List one technique to increase the low-frequency response of a video amplifier. Identify the purpose of various components of the schematic of a complete typical video amplifier circuit. State the purpose of frequency to determine the network of the radio frequency amplifier. State one method the radio frequency amplifier can be neutralized. Identify the purpose of various components of the schematic completing typical of the radio frequency amplifier. Introduction. In this chapter, you will be given the information for the frequency response of the amplifier as well as the specific information video radio frequency amplifiers. All particular purposes, all general information studied in Chapter 1 about audio amplifiers will be applied to the video radio frequency amplifier, which you're about to study. You must be wondering what you need to learn about the video and radio frequency amplifiers. You need to understand the circuits because of the technician who will probably be involved in working with an equipment in which the circuits are used. The many of the circuits shown in this next chapter incomplete would not be the actual equipment. For example, the completing bias network that may not be shown. This is done so you can concentrate with the concept being presented with without being overwhelmed by an abundance of the circuit elements. This idea and amount of information is presented with this chapter, and the real particular information about video and radio frequency amplifiers, the sort of information you will be used to working with. The circuit engineering information such as the design specification will not be presented because it needs not to understand the concept of the technician needs to perform the job of the circuit analysis to prepare. Because you are given the specific information on video and radio frequency amplifiers, you may be able to wondering how these circuits are used. Video amplifiers used to amplify the signal with the representative video information. The term video comes from the video of the picture portion of the television string, the sound portion of the audio. Although the audio is maybe using television, many of the video signals use more than television radio art system. So later in the string series, the video signal, therefore video amplifier, video amplifiers use the video recorder. So some communication control devices, in addition to using video amplifiers to television with radio frequency amplifiers, many other devices such as use of the radio frequency amplifiers, such as radios, navigational devices, communication systems, also any of the devices that use broadcast transmitted information on the radio frequency amplifier. As you should recall, the radio frequency amplifiers used to amplify sound signals between 10 kilohertz and 100,000 megahertz. Do not notice the entire band of frequencies, but any band of frequency within these limits. Therefore, any of the device frequency with 10 kilohertz to 100,000 megahertz will most likely use an radio frequency amplifier. Because you study the details of radio frequency, you determine a little more than about the frequency response, the amplifier frequency response curves. Or amplifier frequency response. Chapter 1 of the module, you will show them the frequency response curve of the audio amplifier. Every amplifier with a frequency response curve that shows you with the technician frequency response curve provided with a picture for the performance amplifier. Various frequencies usually probably near have the draw with the frequency response curve. But in order to use the one, you should know how the frequency response curve is created. The amplifier with which for the frequency response curve is created to test various frequency. It's each of the frequency input signals set with the sum of the determined low voltage current. The same voltage current level, the level of all input signals used to provide with the same input allow the evaluation of the output of the circuit at each of the frequencies tested for each of the frequency output signal is measured, marked on the graph. The graph is marked in the frequency along with the horizontal axis, voltage current along the vertical axis, which points have been plotted. All frequencies tested, and the points are connected to the frequency response curve. The shape of the curve represents the frequency response of the amplifier. Some amplifiers should be flat across the band frequency. In other words, for every frequency within the band, the amplifier should have equal gain with the equal response. For the frequency outside band of the amplifier gain with a much lower. For other amplifiers, the desired frequency response is different. For example, perhaps the amplifier should have a high gain with the two frequencies, low gain with the other frequency. The frequency response curve of the type of the amplifier would show the two peaks on the amplifier and the frequency range response curve. It will only have one peak indicating high gain with the one frequency, lower gain at all the others. Note the frequency response curve is shown in Figure 2.1. The frequency response curve for an audio amplifier described in Chapter 1 is flat from 15 Hz to 20 kilohertz. Okay, so you have 15 and 20 kilohertz flatness band of 19 from frequency hertz. Note in the figure with a low frequency limited labeled frequency 1, upper frequency limited labeled frequency 2. The portion inside of the frequency response is called the bandwidth. You may be wondering what bandwidth is. Bandwidth amplifier. Bandwidth responds to the amount with the width of the frequency band of the frequency the amplifier most effectively amplifying. However, the bandwidth width is not the same as the band of the frequency amplifier. The bandwidth of the amplifier is the difference between the frequency limits of the amplifier. For example, the band frequency band of frequency amplifier may be more than 10 kilohertz or 330 kilohertz and capable of bandwidth of 20 kilohertz. Another example, the amplifier designed to amplify the frequency of 15 kilohertz, 20 kilohertz has a bandwidth equal to 20 kilohertz minus 15 hertz to 19,985 kilohertz. Is shown in figure 2.1. Mathematically, the bandwidth is equal to frequency 2. Frequency 2 minus frequency 1, and you should note that the figure of the frequency response curve show for the output voltage of the current against the frequency lower than the upper frequency of the frequency 1, frequency 2, and over the half power points. Half power points are points at which the output voltage of the current is at 70.7% of the maximum output voltage of the current. Any frequency produced at 70.7% of maximum output voltage of the current is outside the bandwidth, and in most cases, is not considered usable output of the amplifier. The reason these points is called the half power points of the true output power will be half of the 50% of the maximum true output power, where the output voltage of the current is 70.7% of the maximum output voltage. Current is shown below. All the calculation are rounded off to 2 decimal places. As you learned in NEATS Module 2, an AC circuit true power is calculated using resistance over the circuit. Note that the impedance of the circuit produced the maximum output voltage of the 10 volts across the 50 ohm load. Then the true power is equal to the volts squared over the ohms, or 10 volts squared over 50 ohms, which gives you 2 watts. 2 output voltage of the 70% of the maximum voltage of 10 volts is voltage squared over the ohms. 707 volts squared over 50 ohms is 1 watt. You can see these true power with the 50% of the maximum true power for the output with the voltage of 70.7% of the maximum output voltage. Instead, using output current above circuit maximum reading is 0.2 of an ohm, 0.2 of an amp over times the 10. True power is equal to amps squared over the resistance, or 2.2 amps over the 50 watts, or 2 watts. 70% of the output current. The true power is the amps over the squared over the ohms, or 1 watt. One figure 2.1 is 2 points of the marked with the frequency 1 with frequency 2 enable the determine the frequency response limit of the amplifier. In this case, the limit of 15 hertz and 200 kilohertz. You should know see the frequency response curve can be able to determine the frequency limit of the bandwidth of the amplifier. Reading an amplifier frequency response curve. The figure 2.2 shows the frequency response curve of the 4 different amplifier. View 1A, the sample of the frequency response curve shown in figure 2.1. View B, the frequency response curve of the amplifier would be classified as the audio amplifier, even when the curve is down flat from 15 Hz to 20 kHz does not drop off sharply with the frequency limits. From the curve, you can see the lower frequency limit of the amplifier, frequency 1 on 100 Hz, the upper frequency 2, 10 kHz. Therefore, the bandwidth of the amplifier is 10 kHz minus 100 Hz and 99 Hertz. Most amplifier frequency response curves are shaped like view B, but if nothing is done, modify the frequency response characteristic of the circuit, the factor over the effect of the frequency response. The method of modifying the frequency response of the amplifier covered later in this chapter. So the frequency in hertz over the voltage or amps input, the minusing frequency 2 from frequency 1. No, look at view C. The frequency response curve of the radio frequency amplifier. The frequency limits amplifier is 100 kilohertz, 1 megahertz. Therefore, the bandwidth of the amplifier is 900 kilohertz. View D shows another audio amplifier. The time of the frequency of the 30 hertz of 200 hertz. The frequency 2 of the bandwidth of the amplifier is 170 hertz. The important thing to notice with the view D, if the frequency scale is different, on the other view, the frequency scale is again used over the frequency response curve. The scale can also be determined the frequency. They're most useful presenting frequency response curve in a particular amplifier. Frequency response curve and the Q3 amplifier output, the frequency response curve of the Q3 are factors affecting frequency response of an amplifier. Chapter 1 of this module, in fact, with the mention of the auto amplifier limited to the frequency response. Now you will see whether it's true, whether you should recall the frequency response of the AC circuit, the limit of the reactive elements of the capacity of the inductance. In the circuit that is known the capacity called the fact of the capacity of the inductive reactance vary than frequency. In other words, the value of the reactance is determined by part of the frequency in part by frequency. Remember that capacity of reactance is equal to 1 times 1 over 2 pi frequency times capacity, or inductance. The capacity of inductance reactance is 2 pi times frequency times load. If you ignore the amplifier device transistor electron tube, if the amplifier circuit is made up of the resistors only, there should be no limits of the frequency response. In other words, the total resistance circuit would have no frequency limits. However, there are no such thing as total resistance circuits because the circuit components must all have some reactance. In addition, with the reactance of the other components in circuits must amplify the resistor capacitor coupling. This means the capacitor is usually coupled the signal into and out of the circuit. With this, there is also a certain amount of capacity and inductance of wiring circuit that ends of the result. All circuit reactive. To illustrate the figure 2.4. This is the amplifier circuit amplifier circuit with the capacitive inductance for the wiring represented with the phantoms, capacitor, inductors. Reactance for the capacitors and reactance for the capacitors and inductors are shown as the phantom variable resistor. View A shows the circuit of low frequency input signal. View B shows the circuit of the high frequency input signal. Alright, you got a low frequency signal capacitor 1 and adjustable rheostat 1, capacitor 1, and adjustable induction capacitor 1, capacitor 4, inductive capacitor, current rectifier, transistor 1, resistor 2, resistor 1, resistor 2, resistor 3. Resistor 2 has capacitor 2 and inductive capacitation, so C2. Inductive capacitation of L2, induction 2, capacitor 3, induction capacitive 5, induction capacitive. High frequency show the transistor in the middle, resistor 1, resistor 2, resistor 3, grounded, resistor 2, capacitor, capacitor inductive capacitation of the number 1, capacitor 1, inductive inductance of inductor L1, capacitor 4 of the capacitor 3. So on the actual circuit of the components are C1, capacitor 1, 2, and 3, resistor 1, 2, and 3, and transistor 1. Capacitor 1 usually couple the input with the signal. The resistor 1 is developed the input signal. Resistor 2, emitter resistor, is usually the proper biasing and the temperature for stability of the capacitor 2. The decoupling capacitor of the resistor 2, resistor 3 develops the output signal. Capacitor 3 couples the output signal with the next stage of the qualifying transistor 1 amplifying device. The phantom circuit elements represent the capacitive inductance of the wiring. Induction 1, induction 2. Capacitor 4 and 5, and induction 1 represent the inducting of the input wire. Induction 2 represent the induction of the output wire. Capacitor 4 represents the capacitation input wiring. Capacitor 5 represents the capacitor of the output wiring. Alright, in view A, the circuit shown with the low frequency input signal since the formula capacitive reactance, inductive reactance. The capacitive reactance is 1 over 2 times pi times the frequency times the capacitation. Inductive reactance is 2 times pi times frequency times load. You should remember the frequency of the low capacitive resistance. High inductive reactance will be lower. Shown the possible variable resistor represent the reactance. Note the reactance of the L1 and L2 are low. Therefore, do not drop very much input and output signal. Reactance as capacitor 4 and 5 are high reactance bolt lock input outlet signal. Keep from them going from the power supply. VBB or VCC current collector. Note if the output signal is larger amplitude than the input signal. No. Now look at the input signal. The high frequency of the input capacitation is low. The input inductance is high. The input inductance of the 1 and 2 now drop off the input out signal at the same time. Induct capacity C4 and C5 tend short with the pass input with the output signal ground. The net effect of the input output signal is reduced. Notice the output signal is smaller amplitude of the input signal. Now you can see how the capacity and inductance for the wiring affect the amplifier, causing output amplifier to be less high frequency signal with low frequency signal. In addition, with the other circuit component, the amplifying device transistor electronic tube, the effect itself reacts differently to the high frequency than it does lower frequency. In the earlier NEATS modules, you would told the transistor and electronic tubes that have interelectrode capacitancy. Figure 2.5 shows the portion of an interelectrode capacitation transistor, the way in which the high and low frequency signals. 2.5 shows electrode capacitation transistor, capacitor, base common collector, emitter base, resistor 1, resistor 2, low frequency input, high input, resistor 3, Alright, in view A of the transistor show of the phantom circuit with the negative the represent interelectrode capacitation, or CEB, the represents the emitter with the base capacity for the capacitor emitter base represent the base collector capacitation. So we have representative emitter base and then the representative base collector capacitation. For simplicity, view B and C with the capacitive reacting with the capacitor should be variable. The resistor 1 of the capacitator emitter base capacitance, resistor 2 with the capacitor base collector capacitation. View B show the reactance as the high with their low frequency input. In this case, the very little effect of the resistance on the reactance on the transistor. Transistor amplifies input signal with the shown view B with the high frequency low input signal with the ISO amplify the transistor view C. These things somewhat different now. The capacitive reactance low is shown by in setting with variable resistor. In this case, the base transistor attempts to go positive during the first half of the input signal. A great deal of the positive signal is felt on the emitter through the resistor 1. Both base and the emitter go positive at the same time. There is no change in emitter base and bias. Conduction of the transistor will not change. Of course, all the small amount of the change does not occur with the emitter base bias, but not as much of the capacitive reactance is higher at low frequencies, and output signal developed with the collector circuit part of the signal is fed back to the base of the resistor through resistor 2. Signal of the collector is 180 degrees out of phase with the base signal that tends to drive the base negative. The effect to further reduce the emitter bias. The conduction of the transistor during the second half of the input signal, the same effect occurs, although the polarity is reversed. No effect is reduction of the gain of the transistor induction by a small output signal to decrease the amplifier output frequency, higher frequencies coupled with the inner electrode capacitance. The certain special case in which the feedback signal coupled with the inner electrode capacitance is in a phase with the base signal. However, in much case, the feedback causes inner electrode capacitation and degenerated in 180 degrees out of phase with the base signal explained above. Alright, video amplifiers. If you have seen the transistor amplifier limited with the frequency response, you also remember the Chapter 1 video amplifier show that the frequency response of 10 Hz to 6 MHz. This question probably occurred with that. It is probably extended because of the range of the frequency response of the amplifier. High frequency compensation video amplifier. Frequency range of the audio amplifier must extend 6 MHz for the video amplifier so much, and some of the means must be found with overcome the limitation of audio amplifiers. You've seen the capacitation of the amplifier circuit, inter-electrode capacitation, transistor electronic tube cover the higher frequency response to be limited. In some capacitation inductions can be thought of the opposite of the state before the frequency increase the capacity of reactance, decrease the inductive reactance, and increase the capacitation curves. Opposed to change the voltage inductance output with the change of the current. The capacitation causes the current to relieve voltage induction, causes the voltage to relieve the current. Since frequency effect of the capacitive reacting with inductive reactions opposite ways, since the capacitive reacting with the cover the problem, the high frequency response of the inductors are added to the amplifier circuit to remove the high frequency response that called high frequency and compensation inductor coil with the U of the high frequency compensation, also called peaking coil. The peaking coils can be added with the circuit that they are series the output signal path and parallel output signal path. And instead of only in series with the parallel combination, the peaking coils or series parallel output signal can also be used in high frequency compensation. In electrical circuits, nothing comes free. The use of the peaking coils will increase the frequency response of the amplifier circuit, but also will lower the gain of the amplifier. Alright, series peaking. Use of the peaking coil is series the output signal path is known as series peak, then shown with the transistor amplifier circuit. The series peaking coil, the resistor 1 is the input signal developed. The resistor 2 is used with the bias and temperature stability with the transistor 1. Capacitor 1 is the bypass of the capacitor for the resistor 2. Resistor 3 of the low resistor for the transistor 1 develops the output signal of the capacitor 2 is coupling capacitor with a coupled output signal with the next stage phantom circuit of the cut out. Capacitor out represented the outer output capacitation of the circuit with the phantom circuit is a capacitor, and Cn represented the input capacitancy of the next stage. Well, alright, you have the voltage current collector, the ground of the signal going, the source going in the resistor 1, resistor 2, the drain resistor 2 is capacitor, induction, the cutout. Cut in line inductor resistor 4, capacitor 2. You know the capacitive reacting to the cut, the capacitancy out and capacity in input, capacity output and capacity input will limit the high frequency of the circuit and the induction 1 series peaking coil, the shear of the output signal pole, and isolate the capacity output and capacity input of the resistor 4 with a swamping resistor with the U to keep the inductor 1 from overcompensating the narrow range of frequency. In other words, the resistor 4 is U with the high frequency response with the curve flat, with the resistor 4 is not U with inductor 1 there, but there could peak the frequency response curve. Remember that inductor 1 is called peaking coil. Alright, shunt peaking. If the coil is paired with the shunt with the output signal path, the technique is called the shunt peaking. The figure 2.7 shows with the circuit with the shunt peaking coil. The consumption of the atom's capacitor of the N and inductor of the components of the circuit is the same as the figure 2.6. With the resistor 1 with the input signal developing the resistor 2 used bias temperature stability capacitor 1 bypass capacitor for the resistor 2, resistor 3 load resistor for the transistor 1 develops the output signal with the capacitor 2 with the coupling capacitor which coupled the output signal with the next stage. Figure 2.7 shows the shunt peaking. You have the voltage current collector, resistor 3, the inductor 1, transistor 1, resistor 1, input signal grounded, resistor 1, resistor 2, capacitor coil on its own, capacitor 1, resistor 2 on circuit grounded, and then the source going out going to CT, total capacitance with the capacitor 2 and the sim wave. Alright, the phantom capacitor of the CT with the represents total CT represents the total capacity of the circuit. Now the 10 with a couple of output signal to ground. The induction shunt peaking coil with the will interior with the load resistor 3 with the punch parallel shunt with the output signal path. Since inductive reactance increase with the frequency increase with the resistance of the inductance develop more output with the signal frequency increases at the same time with the capacity of reactance the total capacitance decreasing frequency increase that depends on the tends coupled more output signal to ground with increase the inductivity reactance counters the effect with the decrease the capacity of reactance increase with the high frequency response amplifier. Combination peaking. You have seen with the series peak with the coil isolated with the output capacity of the amplifier with the input capacity for the next stage. You also seen how the shunt peaking coil with the counteract with the effect of the total capacity with the amplifier. If these two techniques are used together, the combination is more effective for than using either one alone. Use both series with the shunt peaking coils known to the combination peaking amplifiers for combination peaking is shown in figure 2.8. In the figure 2.8, the peaking coils, the induction 1, induction 2, induction 1 shunt coil peaking, induction 2 series peaking coil. The phantom capacitor total capacitance of the amplifier circuit. The phantom circuit with the capacitor input represents the input capacitation next stage combination. Peaking will also allows an amplifier to have high frequency of response at 6 megahertz. Alright, low frequency compensation for video or amplifiers. Know that you have seen the high frequency response of the amplifier can be extended within 6 megahertz. You should realize that only the necessary to extend the low frequency response to 10 hertz in order to have the video amplifier. Once again, the culprit of the low frequency response with the capacitation or capacitive reactance bump at the time of the problem is coupled with capacitor between the stages. The low frequency the capacitive reactance with a coupled capacitor of the G2, the figure 2A, is high. The high resistance reactance limited amount with the output signal with the coupled to the next stage. In addition, with the RC network, the coupled capacitor signal developed resistor next stage for the phase shift. The output signal versus the NEAT module 2, the discussion phase of the resistor capacitor networks. Both of these problems poor low frequency response phase shift and can be solved by adding a parallel resistor capacitation here with the low resistor shown in figure 2.9. Or your complete circuitry of the transistor Q2 transistor Q2 is not shown in figure main term of the signal developed in the resistor 5 of the transistor 2, the coupling capacitor C2 and the resistor 5 limit the low frequency range response for the amplifier couple. The phase shift, the amount of the phase shift will depend upon the amount of the resistance capacitation resistor coupler network of the resistor 4 and capacitors 3, compensating for the effect of the capacitor 2 and resistor 5, the effect of the low frequency response of the amplifier. At low frequency, resistor 4 adds the load resistance of the resistor 3, increase the gain of amplifier as the frequency increases. They react with the capacitor 3, with the capacitor 3 provides the path around resistor 4. Gain of the transistor decrease at the same time the reaction to the coupled capacitor decrease the more with the single coupled with the transistor 2. Because of the circuit shown in figure 2.9 with no high frequency compensation would be very practical video amplifier. Typical video amplifier circuit. There are many different ways in which the video amplifier can be built. The bit of particular configuration video amplifier depends on the equipment of the video amplifier used. The circuit shown in the figure 210 is only one of the possible video amplifier circuit. Rather than reading them about each of these circuits, you should see how they are learned with the video amplifier by answering the following questions. You should have no problem identifying the purpose of the components because of the similar circuits that have been explained earlier in the text. Alright, radio frequency amplifiers. Now you have this scene with the way of the broadband with the video amplifier can be constructed. You made it can be one of the radio frequency amplifiers. You have the same technique or just another type of the radio broadband. Do they use the same technique or are they just another type of the broadband amplifier? The answer to both questions is no. Radio frequency amplifiers are different techniques have the video amplifiers very different to them. Before you have the specific technique for the radio frequency amplifier, should review some of the important relations between input and other impedance amplifiers, gain, amplifier, stage. Amplifier input, output, impedance, and gain. You should remember the gain of the stage calculated with the input and output signal. The formula calculated with the gain and stage gain is equal to output signal over the input signal. The voltage gain calculated input output voltage. Current gain is used the input and output current. The power gain is used the input and output power. The purpose of our discussion will only be concerned with the voltage gain. Figure 211 shows a simple amplifier circuit with the input and output signals developing into impedance presented with a variable resistor with a circuit with a capacitor 1, capacitor 2, input output coupling with capacitor, resistor 1, impedance the input circuit 1, resistor 2 represents the input signal developing impedance, resistor 3 represents the output. So you have voltage voltage collector. Resistor 2, variable resistor, resistor 1 capacitor, resistor 3 variable, capacitor 2 ground, resistor 1 and resistor 2 voltage divider net with the input signal with the resistor 2, increase the value with the input signal with the transistor 1, increase the cost of the low or larger output signal with the gain of the change, increase the look at the output the resistor 3, increase the voltage output signal, increase and also increase the gain of the stage. As you can see, increase the input signal developing impedance for the output impedance, both increase for the gain stage. Of course, these are to the limits for the process of the transistor. The transistor must not be overdriven in a high input signal, and distortion will result. With the principle in mind, you could design a circuit that has more impedance, specific frequency, band frequency. The circuit could be you use the radio frequency amplifier frequency to determine the network. Could be either the input signal developing impedance for the output, but the impedance for the radio frequency amplifier circuit would have been shown figure 212. Alright, in this semi-block diagram, C1, C2 are the input-output coupling capacitors, representing the impedance input circuit with the block of the FDN, representing the frequency determining network. These reviews the input signal developing output signal with the transistor 1. Alright, frequency determining network for a radio frequency amplifier. What kind of a circuit would be active with the frequency determining network? In general, the frequency determining network is a circuit developed with the desired response with a particular frequency. The response could be a maximum impedance, minimum impedance. It all depends on how the frequency determines the network. You will see the more of the frequency determining the network is the Nice module and introduction wave generation shaping circuits. If you've seen the frequency determining network near the radio frequency amplifier, you'll have the maximum impedance of the desired frequency before you show them the actual component of the make of the frequency determining network of the radio frequency amplifier. Look at figure 213 with a simple parallel circuit with the resistor of the circuit is variable with the N are connected together and gain in which way the resistor 1 increase the resistance of the resistor 2 increase the vice versa. Figure 213 shows a parallel variable the resistor gained. Each resistor ranges from 0 to 200 ohm, following the relationship that exists between the individual resistance of the network RT, all the value of the resistor resistance of the and the network rounded off the 2 decimal safe the selected value of the infinite number of the possible combinations. As you can see, the circuit of the maximum resistance of the total individual resistance of the equal the value of the variable resistor representing impedance of the component that can be found with the variable varied in the impedance the same way the gain resistor figure 213 you would have the frequency to determine the network need of the radio frequency amplifier. Therefore, the components vary with the impedance of the reactance length with the like the gain resistor for the as you have known if the resistance the inductor the capacitor vary inductive frequency change the frequency increase the inductive reactance increase the capacitive reactance decreases. At some frequency, inductive capacitive reactance will be equal. The frequency will depend upon the value of the inductor capacitor. If the inductor capacitor will connect with the parallel inductive circuit, will have the ideal frequency to determine the number of the radio frequency amplifier. The parallel induction circuit capacitor circuit is used with the frequency to determine the network is called the tune circuit. It is named in the tune to give it the proper response to the desired frequency, select the proper value of the inductance capacitance. Circuit used the principle is shown figure 214 show the radio frequency amplifier parallel the inductive capacitor used with the frequency to determine the networks. Radio frequency amplifiers will only affect the amplifier frequency to determine the parallel inductive currents. Alright, L1 and L2 and C3 and L2 are your tune circuits, voltage current collection, transistor 1 capacitor, image capacitor 4 is the split. is many electronic devices, radio, television, receive the radio system of the particular frequencies like of the band, and frequently could be done the use of separating radio frequency for each frequency, turning the appropriate radio frequency amplifier more efficient with the effective single resistor radio frequency amplifier tuned with the particular frequency of the frequency needed. This is what happens when you select a channel on your television or tune in the station on your radio. To accomplish the tuning, you need only change the value of the induction capacitation parallel with the inductive circuit and the tuned circuit. In most cases, the capacitation chamber, the use of variable capacity of the capacitor is in the output of the portion of the radio frequency amplifier stated, getting together in order that they can all be changed at one time in the signal device and tuning the dial of radio. The techniques will be shown in the schematic a little later in this chapter. Alright, radio frequency amplifier coupling. Figure 214, other circuits have been shown the use of capacitor to couple the signal into and out of the circuit C1 and C4, figure 214. Remember the chapter 1 that there are also the method of coupling signals one stage to another. The transformer coupling, most uncommon use of the coupled radio frequency amplifier transformers, coupling many advantages over the radio resistor capacitor coupling for radio frequency amplifier. For example, the transformer coupling with a few component with the capacitive coupling. It can also provide means of increasing gains of the stage of using it as a step-up transformer voltage gain. If the current gain is required, a step-down transformer can be used. You should also remember the primary and secondary windings of the transformer. Inductors will define factors mind with the amplifier could be constructed like one shown in figure 215. Transformer coupled with a radio frequency amplifier shows the capacitor voltage emission current transistor 1, transistor 2, coupling capacitor 1, and transformer winding 1. In the circuit of the secondary transformer winding 1, capacitor 1, the tuned circuit with the input signal with the developing impedance of the primary transformer winding 2, capacitor 2 tuned circuit is input output with the impedance of the transistor 1. Both transistor 1 and transistor 2 must be radio frequency transformers in order to operate the radio frequencies. The input signal applied with the primary transformer 1 could come from previous stages from some point of the input device and receiving the antenna. Then the input device with capacitive connected. Across the coil, they're from the tuned circuit in the same way. The secondary transformer output with the circuit of the capacitor connected on the secondary transformer would pair with the inductive of the capacitor network. Network could act as the input signal developing impedance. The next stage of the network could represent some type of the output device and transmitting antenna. The tuned circuit form of the transformer capacitor must not have the bandwidth required by the amplifier. In other words, the bandwidth of the tuned conservative may be tuned over the requirements of the amplifier. For example, the radio frequency of the television receiver that usually require bandwidth of the 6 MHz. One way to broadening and band of the tuned circuit is using swamp resistor. This is a similar way to the swamping resistor that's shown with the receiver. The peaking coil with the radio amplifier. The swamping resistor is connected to the parallel tuned circuit with such as a much broader band base. Bandpass. The technique of the theory behind the discussed is in each module 9. Another technique to use the broadened bandpass is involve the amount of coupling in the transformer. The transformer term in coupling refers to the amount of the energy transformed from the primary to secondary transformer. This depends on the number of the flux lines from the primary intersects the uncut and secondary. With the more flux lines of the secondary, more energy is transferred. Coupling is main function of the space between the primary and secondary windings. The transformer can loosely coupled to have little transfer energy output coupled to just as right amount of the energy transferred to overcoupled to the point of the flux line. Primary and secondary windings interfere with each other. Figure 217, view A, view B, view C show the effects of the coupling and frequency response of the induction capacitive circuits that may have been made for primary and secondary winding transformers. Alright, A shows the effects of the coupling frequency response, loose coupling frequency, output, optimum coupling, effective coupling frequency, optimum coupling frequency, overcoupling, effective coupling and frequency, coupling. In view A, the transformer is loosely coupled. The frequency response curve shows the nearer bandwidth of view B with the transformer output coupling the bandwidth of the wire with the curve is relatively flat. The view C with the transformer that overcouples the frequency response curve with the broadband pass. The curve of the dips of the middle showing the freeze frequency are not developed as well over the bandwidth. The optimum coupling will usually provide the necessary band pass for the frequency to determine the network. Therefore, the radio frequency amplifier for some of the such radio frequency amplifiers, the transistor television receiver band pass available with the optimum coupling is not wide enough. In this case, the swamping resistor, as mentioned earlier, will be the optimum coupling, the broad band pass. Compensation for the radio frequency amplifiers. No, now you have been shown the way of the radio frequency amplifier figure to amplify with the band of the frequency and with the radio frequency amplifier in tune with a particular band of the frequency. You also have some of the way of the bandpass radio frequency amplifier can be adjusted. However, the frequency of the radio frequency amplifier operates in a high certain problem exists. One of the problems loop that occur with the transformer high frequency, and another problem with the electrode capacitation transistor process over there. Common these problems not compensation. Or a transformer and a radio frequency amplifier. As you recall, that needs module 1, the loss of the transformer clove, the copper loss, the eddy current loss, the hysteresis loss of the copper loss, effective of the frequency dependent of the resistance of the winding current through the winding, similar eddy current loss, mostly function in inducing voltage rather than frequency from the over the voltage. Historically, the loss, however, they increase the frequency increases. Higher hysteresis loss include the realignment of the magnetic domain of the core of the transformer each time the polarity magnetic field change. The frequency of the AC increase with the number of the shifting magnetic field of the cross of the two shift the H of IAC cycle. Therefore, the molecular friction increase with the hysteresis loss is greater than the increase with the hysteresis loss cover the efficiency of the transformer. Therefore, the amplifier decreases. The energy that goes through the hysteresis loss to take away from the energy could be going into the signal. Radio frequency transformer, specially designed for the radio frequency. Are you the current problem with the exterior of the life of the transformer of the radio frequency amplifier? The winding with the radio transformer frequency transformer is wound only on the tube non-magnetic material. The core is either powered iron or air. The types of cores also eddy current. Alright, neutralization of the radio frequency amplifiers. Alright. Problem in the electric capacity of the transit of the radio frequency amplifiers is solved with the neutralization and process of counteracting neutralizing the effects of intra-electric capacitation. Figure 2.17 shows the effect of the base collector, intra-electric capacity, the radio frequency amplifier capacitor, and the phantom capacitor CBC represents the inter-electric capacitation between the base of the collector of the transistor and the inter-electric capacity of the most effective radio frequency. As you can see, the phantom capacitor causes the negative degenerated negative feedback with a discrete gain of the amplifier. Therefore, in some cases, the phantom capacitor can cause regenerated positive feedback. In this case, the technique is discussed to provide negative feedback with accomplished neutralization of the amplifier. As you may recall, on one of the degenerated feedback can be counteracted neutralizing the using positive feedback exactly with doing the neutralize the radio frequency amplifier. Positive feedback accomplishes feedback capacitor must feedback signal in the face of the signal of the face of the transistor. One method of doing so is shown in figure 218 feedback capacitor C4. It has been added neutralizing the amplifier to solve the problem on when a degenerated feedback except for the capacitor 4 is identical to the circuit shown in figure 217. The phantom capacitor called the regenerated feedback capacitor 4 stay neutral over the amplifier. This is true because capacitor 4 allows the feedback signal in 180 degrees out of the phase of the feedback, a signal of the phantom capacitor. Alright, your typical radio frequency amplifier circuits. As a technician, you will be many different radio frequency amplifier, different piece of equipment. That particular circuit configuration of the radio frequency, it will depend upon the amplifier used in the final part of the chapter shown with the typical radio frequency amplifier circuits. Figure 219 shows the schematic diagram of the typical amplifier with the AM radios received. The figure 219 input the circuit with the antenna radio inductive coil number 1 shows the part of the inductive capacitive circuit. Tuned with the desired station variable capacitor 1, inductor 1 wound in the same core, inductor 2, which causes the input signal of the capacitor 2 with the transistor 1. Resistor 1 provides the power base of the transistor 1 from base power supply, and resistor 2 provides the power base of the emitter with the transistor 1, the capacitor 3 with the bypass resistor 2 primary transformer winding 1, capacitor 4 with a parallel inductive capacitive circuit which acts as the load of the capacitor transistor 1. The inductive capacitor circuit is tuned by capacitor 4 which gained the capacitor 1 allowed the antenna. And inductive capacitor circuit is tuned with together the primary transformer 1 center tap providing impedance matching with the transistor 1. Or your typical AM radio frequency amplifier. The gain capacitors are CM4 on the inductive lining, inductive and local density of antenna 1 and 2 are the one on the antenna. The gain capacitor also goes through the transformer winding C4 and the voltage current capacity common collector. of the transistor 1, and from the antenna C capacitor, the induction 1 and 2 goes to C2, resistor 1 to voltage by power supply, transmitter, resistor 2 and capacitor grounded, and output through the transformer as an amplifier. You may notice no neutralization shown in the circuit. The circuit is designed with the AM broadcast of the 535 kilowatts over the 16,000 kilohertz. At a relatively low frequency, the degenerate feedback over the base to the collector inner electrode capacity is minor. Therefore, the amplifier does not need neutralization. Figure 220, typical amplifier used with VHF, VHF television. Receive the input signal developing the circuit with the amplifier of the induction 1 capacitor 1 capacitor 2, the inductor 2 with the independent signal developing the capacitor proper television TV channel. The inductor 1 can be switched off of the circuit with another inductor switch in the circuit of the channel. Select the resistor 1 provides the power base for the transistor 1 with the power supply, VB, the transistor 1 sold, the transistor over the K for the transistor 1 dot circled around the transistor symbol, shown to be the ground. The K for the B must be ground because of the high frequency of 54 megahertz to 270 megahertz used by the circuit. The resistor 2 provided the proper bias for the emitter of the transistor 1 with the capacitor 3 into the bias for the resistor 2, capacitor 5 induction coil L2 are paired with the induction capacitive circuit which occurs on the low of the transformer. 1 the L induction capacitive circuit is tuned to the L inductive capacitor 2, which is switched into the output of the induction capacitive circuit. The channel selector the inductive and capacitive inductive 3 and capacitive 3 parallel the LC current circuit developed at the signal next stage. The parallel LC circuit is tuned to the inductive L3, which is switched in and out of the bank of the LC circuit. The channel selecting along with the L1 and L2, L1, L2, and L3 are actually part of the bank of the inductors. L1, L2, and L3 are circuits when the channel selector is on channel 2. The other channels, another group of 3 inductors would be used in this circuit. The resistor develops a signal through the capacitor for proper neutralization counter effect for the inner electrode capacitation from the base of the collector of the capacitor is something isolated with the voltage from the collector's power supply. Right, you have your collector power supply, grounds 8, capacitor 1, capacitor 3, and resistor 2, capacitor 7, capacitor 6, output signal, capacitor, induction 2, induction coil 3, input signal, output signal, typical radio frequency amplifier. Summary of Chapter 2.